This video is part of the lecture for multivariable calculus, and I'm going to talk about tangent lines and tangent planes. So let's start. I'm going to give you a recall first. If we have a function of one variable, the tangent line to y equals to f of x at the point x naught and y naught, where y naught is basically the value of the function at x naught, is equal to that. So let me graph it first. I have x-axis, y-axis, and I have y equals to f of x. At the point x naught and y naught, I have a tangent line, and the slope of this line is derivative of the function at the point x naught. And if we know the slope, writing the tangent line would be easy because I have a point, I have the slope, the point is x naught, y naught, and then the slope x minus x naught. Okay, so that's equation of the tangent line. Now we say that linear approximation is easier after that. It's just because if the point x, let me pick a point x, is very close to the point x naught, the value of the function at the point x is equal to f of x, which is right there. And as you see, it's very close to the value of the tangent line at the point x. Since x is very close to x naught, then the approximation would be a good approximation. So we're going to say that if x is very close to x naught, then the value of the f at x is approximately the linear approximation at the point x. What is the linear approximation? I'm gonna look at the tangent line, and I'm gonna bring y naught on the other side. So y would be equal to f prime of x naught, x minus x naught, plus y naught. And y naught is basically the value of the function at x naught, which is f of x naught. Okay, so I'm gonna call this one L of x. Okay, so it would be equal to f of x naught, which is basically y naught, plus f prime of x naught, x minus x naught. Okay, very good. So that was the tangent line to the curve of just one variable function. So let's look at if we have a surface, a function of two variable, then we're going to have tangent plane instead of tangent line. So let's see how we can define this. Now that we have two variables, okay, we have tangent plane to z equals to f of x and y at the point x naught, y naught, and then z naught, which is basically the value of the function at x naught and y naught. So let me graph this situation as well. So I have x-axis, I have y-axis, and I have z-axis. And let's assume that, for example, this is the surface of z equals to f of x and y. Then at, for example, this point in here, I have a tangent plane like this. That is, this plane is tangent to the curve z equals to f of x naught. The the surface at the point x naught and y naught. Okay, and as you see, we have partial derivative of f with respect to x. This is basically the slope in the x direction at the point x naught and y naught. It's basically the slope in x direction. Then I have like partial f partial y at the point x naught y naught is the slope in y direction. Okay, and this is basically the point that I have in here is x naught y naught, and then the z coordinate, which is d naught. Now if we want to kind of repeat kind of similar situation as you see, then I can say that the total displacement of z, which is z minus z naught, is equal to the partial derivative of f with respect to x at the point x naught and y naught at x minus x naught plus slope in the y direction at y minus y naught. Okay, as you see, this is equation of the tangent plane at the point x naught y naught and z naught. So partial derivative x minus x naught, partial derivative with respect to y minus y naught, and plus z naught. Okay, so this is basically equation of the tangent plane at the point x naught y naught and then z naught. So it's a plane. I have a point. If I can write or basically remember the normal vector, it would be very good to write equation of that. And as you may notice, the normal vector to that, so let me write the normal vector, is partial derivative of f with respect to x at a given point, partial derivative of f with respect to y as the second coordinate, and then let's pick -1 for the third coordinate. You can also pick 1, but I'm gonna pick -1 to be exactly the same equation. As you see, if you remember that as a normal vector, you can write equation of the tangent plane without even memorizing that. Okay, now the linear approximation. If the function f is differentiable, which I'm gonna explain in the next video, if the function f is differentiable and the point is very close to the point x naught, y naught, and z naught, then the linear approximation would be this. So the value of f at the point x and y, where the point x and y is very close to this point, is equal to L of x and y. What is L? L, the linear approximation, is exactly the equation in here where I bring -z on the other side. So it would be partial derivative of f with respect to x at x naught, y naught, x minus x0, plus partial derivative of f with respect to y at the given point, and then y minus y naught, plus I'm gonna bring z naught on the other side. And what is z naught? Z naught is basically f of x naught and y naught. Okay, so that was the linear approximation using the tangent plane.